Ladies and gentlemen, hello and welcome, coming to you not quite live from One Take Studios, where today I have a topic that I kind of enjoy. Alright, so this is going to be permutations and combinations. Permutations and combinations. And this is one of like the basic entry-level ideas for probability. Alright, so let's see if we can get these foundation blocks in place and keep them straight. So, first of all, let's do some comparison, shall we? Permutation versus combination. So what do we got going on? Permutations are groups of objects, and combinations are groups of objects. Excellent, excellent. Except that we can't tell them apart. So, now what? Here's the big one, ladies and gents. This is the big one, all right? In a permutation, the order of your objects matters. In a combination, the order of your objects does not matter. That is the key difference between these two. All right, order matters for a permutation. Order does not matter for a combination. This is how you're going to keep these two things straight, okay? All right, so let's see. Let's think of something that might help your brain remember this. What is something that everybody in high school uses that is a word that gets used wrong all the time? Most people have a locker. Lockers are usually locked, and they have some sort of locker combination to get into them. Guys, just think about this for a second. Many locker combinations have 3 numbers. Does the order of those 3 numbers matter? If my locker combination is 1, 2, 3, can I use 3, 2, 1 to get into it? No. We as a society use the word combination incorrectly. So if we're thinking about examples here for a moment, ladies and gents, a locker combination is technically a permutation. So I'm going to put in quotation marks here, locker combination. Locker combination isn't a combination at all. It is a locker permutation. All right, so maybe you can use that to kind of keep these things straight in your brain. This is not a locker combination, it's a locker permutation. Ha! I dare you to go into the office and say, hey, Mrs. So-and-so behind the desk, can you please tell me what my locker permutation is? That would make me happy if you did that. All right, so let's think of another example. What about ice cream toppings? Ice cream toppings. Does the order matter? If I put a whole bunch of different things on my ice cream, does the order matter or not? Well, some people might try to be really stubborn and say, yes, the cherry must go on top, but does it really need to? I don't think so. So, in that case, ice cream toppings would be a combination. That's an E, ice cream toppings. All right. Other examples. Officers. You run for office, president, vice president. Is that a combination or a permutation? Does the order matter? Well, think of it this way. If I've got a president and a vice president, and they switch, is it different? Technically, yes. Now, depending on how your particular officers work their particular jobs, I don't know. But if everybody assigned a specific role and I switch it, that means that order actually makes a difference. So class officers would fit in the category of a permutation. Well, what if I've got my student council going on here, and I'm not talking about class officers? What if I'm talking about a committee? All right, we need somebody to make posters for the hallway. Is that a combination or permutation? Well, if I've got a group of people and they're all working on making signs, does it really matter which order those people are in? If we switch them, are any roles reversed? No, not in this case. So a committee of people would actually fall under the category of combination. And I'm trying to remember how to spell the word committee. I think that should be correct. There we go. All right. So a couple of examples there maybe to help your brain keep these sorted out. Permutation order matters, combination it does not. All right. Next thing I'd like to talk about is you haven't done laundry in a while. Actually, I'm doing laundry right now, but that's a different story. If you haven't done laundry in a while, you don't have a whole lot to wear, you might look in your closet and say, I have nothing to wear. Not technically true. Oh, by the way, not only have you not done laundry, but the dog has eaten most of your shoes and you only have 2 pairs of shoes left. So let's look at what's left in your closet. As far as clean stuff, you've got a pair of jeans, a pair of sweats, you've got a blouse, a tank top, and a hoodie, and a pair of Crocs and a pair of gym shoes. That is all that's in your closet. Okay, I'll play. Let's say that you have nothing to wear. All right, nothing to wear. I'm going to beg to differ on that one. Okay? I have made a delightful, delightful tree diagram of all of your options. All right, check this out. We have so many options. So from the beginning, we're going to make a choice. We can either choose the jeans or the sweats, as we can see our two pant options here. And let's say I choose the jeans. Well, now I can pair that with the blouse or the tank top or the hoodie, any of these three choices. And let's say that I choose the jeans and the blouse. Now I can pair that with Crocs or gym shoes. Are these all outfits that you would wear out of the house? Maybe not. Maybe so. That's up to you. But I want you to look at this. Having nothing to wear actually results in how many different outfits. So if you follow, that's one path, that's two paths, 3, 4, 5, 6. Ladies and gentlemen, if you go to the ends of all these branches, you actually have 12 different outfits that you could wear. That's not nothing, that's something. So let's think about this. How might we possibly figure out that we've got 12 outfits without drawing a tree diagram every single time? Because that gets to be a bit much. Well, let's see. We had 2 choices here for pants. Whoops, don't peek. And 3 choices here for tops. And this marker's not showing up very well. 2, marker, pen, whatever it is. 3 and 2. Any ideas yet as how we might generate the number 12 if I had 2 choices, 3 choices, and 2 choices? Ladies and gents, what is 2 times 3 times 2? That gives us a grand total of 12 outfits. There are 12 outfits in my closet, despite the fact the dog has chewed my shoes and I have no clean clothing. Alright, so what is that? How does that come into play here? Well, that is actually what's known as the fundamental counting principle. It does go by other names, so if you see it under a different name, don't worry about it, it's fine. But the idea is that you're going to multiply the number of ways that each event can occur. That's a number. Multiply the number of ways each event can occur. Choosing a pair of pants was an event. It could occur 2 different ways. Choosing a top was an event that can occur 3 different ways. Choosing a pair of shoes was an event that can happen 2 different ways. 2 times 3 times 2, 12. That is the fundamental counting principle. For people that are looking at tree diagrams, oftentimes people don't understand really how to structure these very well. You always have a starting point, but each set of branches is a choice. So since I had, for this particular event, 2 options. This right here is event 1. This is choice number 1, and it can wow, choice number 1. Much better, much better. And this can happen 2 different ways. So my next set of branches represents choice number 2. Choice number 2. That I can go with blouse, tank, or hoodie. These can occur 3 ways or 3 ways. And then my third set of branches is choice number 3. And again, down the line for all of those. So branch, choice, 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 choice. There we go. All right, so we've got combinations and permutations. We've got the fundamental counting principle. What else is fun and exciting? All right, so let's see if we can't maybe pull a couple of these ideas together, shall we? Permutations. Let's go back to permutations for a moment. Let's move this guy out of the way. All right, so we've got 3 spots on a shelf, and we have 3 objects. And we're looking at this going, I would like to arrange these objects on my shelf, but oh man, there's just so many choices. What could I possibly do? All right, well, let's think about this. I like to think of this as sort of like fill in the blank. All right, so here is spot on the shelf number 1, spot on the shelf number 2, and spot on the shelf number 3. If I have 3 objects, how many of those could go in the first spot? Quite frankly, any of the 3 could go in that first spot. So we're going to put 1 object there. Now we're going to go to fill the second spot on the shelf. How many objects do I have left to choose from? Well, if I put 1 of the 3 objects here, now I only have 2 objects left to put in this spot. And I choose 1, and now I only have 1 object left to fill the last spot. Choice, choice, choice. Number of ways it can occur, number of ways it can occur, number of ways it can occur. Ladies and gentlemen, this is, sneak, the fundamental counting principle at work. If I simply multiply these together, 3 times 2 times 1, that is 6. There are 6 different ways that I can arrange the object on the shelf. Notice I just used the word arrange, so 6 arrangements. What does arrangement imply? Order matters. All right, so we're talking all permutations right now. Order matters. So there's 6 different arrangements that could happen for 3 objects on the shelf. Okay, well, so let's say I've got a lot more stuff. Let's say I've got 3 spots on a shelf, but I have 10 objects. What's the difference? Well, spot number 1, spot number 2, spot number 3. Okay. I have 10 objects total, so how many could I actually choose from for the first one? That first choice could go 10 different ways because I have 10 different things to choose from. In the second spot, I will have used one of the 10. Now I have 9 objects remaining to choose from, and then I will have 8 objects remaining to choose from. So again, I do this, and I get, ooh, crazy, 720 different arrangements. So if I have more objects to choose from, I have a lot more options to decide from. Alright, so this is an overview then of what we might see for the numbers of arrangements, and there's essentially two things that just happened here. Thing one is if I am using all objects. So example number 1 here says I'm using all objects. I have 3 spots, I have 3 objects, I'm going to use everything. How do I calculate that? A little something that's called factorial. And I use the exclamation point on purpose because, ladies and gents, that's how mathematically you write that. Alright, we have 3 objects here, so what we actually did was 3 factorial. We did 3 times 2 times 1. That is what 3 factorial means. 3 times 2 times 1, which was 6. What if I had 20 objects and I wanted to use all 20 of them? Factorial. 20 factorial. 20 times 19 times 18 times 17, 16, all the way down to 1. Alright? So that's what a factorial is in math. You take your highest number and then just keep multiplying from on down. Consecutive integers, there we go, all the way down to 1. Don't use 0, that'll wipe everything out. So anytime you have all objects in use, you are going to use a factorial. Alright, what if I don't want to use all my objects? Alright, so what if I'm using some of my objects? Does this method work? Yes, and quite frankly, my brain usually processes it this way. But in case you're looking for something more complicated to work with, what if I use this formula instead? Alright, this right here is the formula that we use. I call it the NPR formula. When I want to use some but not all of my objects. P is for permutation. N is the total number of objects. So if I go with this second example here where I was only using some of my objects, I would have 10 as N. And then R is a subset, the smaller group. So out of the 10, I'm using 3. So N would be 10 and R would be 3. What happens if you do 10 factorial over 10 minus 3 factorial? A bunch of stuff cancels out and you're left with 10 times 9 times 8. So this is just really a slightly different approach to what we've seen for processing this right here. Alright, but reason that some people like it, it is in the calculator. So let's check that out for a moment here. Everything fun and exciting as always in the menu. There's my menu. And since we're working the basics of probability, we want to go there. Oh, hey, look, there's factorial. Well, okay, let's take a quick diversion there. Oops, that's right. That's right. You would have to do 3 and then go into the menu if you wanted to use 3 factorial. So there we go, and enter 3 factorial. Excellent. Alright, but if I want to use my other one here, menu, probability, so let's say I'm going to go with my permutations on this. Notice I said it's an NPR formula. There's the N, there's the R. You have to tell the calculator what the arguments are. That's what you call these numbers in parentheses. You have to say, I have 10 things, and out of the 10 things, I would like you to use 3 of them. Those are my arguments for this particular formula. And we hit enter, and there is 720, which was the same thing that we got moments ago. Right, oops, wrong screen, this one right here. Right there, 720. So this is something that the calculator can use kind of nicely. Maybe you like it, maybe you don't. Maybe your brain prefers this. I know that mine does. Alright, so next up, what if we process the same material, but we process it for combinations instead of permutations? Alright, so what changes? What's going to be different here? Alright, so let's see. Combinations. Order does not matter. And I have 3 movies I'd like to see, and I'd like to see 3 of the 3. So I'd like to see all 3. And my focus is crazy. Okay. So what happens? Let's call them movies A, B, and C for a moment. Alright. So let's see. How many different ways can I see that group of movies? Movie A, movie B, movie C. I could rearrange them. I could see movie B first, but wait a minute. Order doesn't matter. So what if I see movie C first? Oh, wait a minute. Order doesn't matter. I would like to see all 3 of these 3. How many groups can I make? If order doesn't matter, how many groups can I make using all 3 of these? I'll give you a clue. That's a group. And that's the only group that I can make using all three. So if I want to see 3 of 3 movies, there's exactly 1 combination. And so, while it's interesting to use all objects in a permutation and you can get different results, if you are talking a combination and you are using all objects, the answer is always the same. If you're using all objects in a combination, there can only be 1 combination. That's it. There's no other way to work with that because arrangements don't matter. Alright, so on to something slightly more interesting. Let's see that I'd like to see 3 movies, but there are 5 that I want to see. So out of 5 movies, I'd like to see a group of 3. If order doesn't matter, I just need to start making groups of 3. Well, here I could only make 1 group of 3. How many groups of 3 can I make here? Well, let's see. That's still a group of 3. But wait a minute, that's a group of 3 there. But that's also a group of 3 there. And what if I do this one with this one and this one over here? This could get really messy really fast. How many groups of 3 do you think I can make? Wouldn't it be nice if there was a formula so that I didn't have to make a mess of this? I think so. So, if I'm using some objects for a permutation, I have an NCR formula, all right? An NCR formula. C, again, is for combination this time, and the N and the R are the same thing. So N is going to be my total number of objects, and R is the subset that I'm using. So this is N factorial over R factorial times N minus R factorial. And so if I want to work that with this, let's just think about how those numbers would plug in for a second. That would be N, that's all of them, so that would be 5 factorial. That means 5 times 4 times 3 times 2 times 1, over R factorial, that's 3, that's my subset, 3 times 2 times 1, and then N minus R, so 5 minus 3 factorial. So that's actually 2 factorial, and I would have to calculate it that way. A little bit obnoxious, but again, guess what? This is also in the calculator. So check this out. If I go back to the screen right here, there we go, and I say, all right, again, back to my menu, back to probability, sure enough, there's something here that says combinations. And oh look, there's NCR. So I said that there are 5 movies total, and out of the 5, I'd like to see 3, but the order to me does not matter. So therefore, 10. That is the answer to our question from earlier. How many groups of 3 can I make? I can make 10 groups of 3. And so that is our NCR formula. So jumping back right there, there we go. All right, so grand total, oops, I put 0. I meant to write 10, I forgot the 1. All right, so that means that there are 10 different groupings that I can make here of 3 at a time. And I can do this without making a giant mess and confusing myself. All right, so recap of things, essentially, know what permutations are, order matters, Locker permutation, not combination. Know what combinations are, order doesn't matter. Know what the fundamental counting principle is. We touched on factorial, and then we've got 2 new formulas for this as well. So know it, love it, watch the labels, pay attention. All right, pay attention to details and have fun. Bye.